Swayam Prabha. Digital India. Educated India.
Dear friends, welcome back once again to the lecture on system engineering. In the last class we discussed about the modeling techniques, especially on the behavior modeling. How do we see the dynamics of the system or the behavioral dynamics of the system, and how do we model it using graphical modeling techniques. We discussed about the Petri net, which is one of the important tools for modeling the dynamics of the system, and we saw the basic elements of place, transition and the arc to represent the dynamics, and we saw one simple example also. I will take you through a few more lectures where actually we will try to see some complexities, concurrencies in the system, and then activation of some control elements, control signals to start the process or start the transition. So we will go through some of the examples and then show you how the Petri nets can be used for complex systems and modeling the dynamics of complex engineering systems. Let me take a simple example. So before going to that, let me just explain to you this point once again, because in Petri net we use the Petri nets to understand the reachability of a system, whether we can reach a particular state from an initial state. So what are the transitions needed to reach that state, so that can be analyzed. Similarly, the boundedness of a particular state. So to what extent we can continue to load that particular state, or when we do, should we actually stop that transition to that particular state because there may be an overflow of data or information. So how do we actually check that boundedness of a system? So this also can be tested using Petri net. Then we have this liveness of a system, whether the system transition will lead to a death of a system in terms of whether the system will stop giving an output or there will not be an output when we reach a particular state. These are all can be modeled using Petri net. Apart from this, we can actually see that there are multiple local states which actually lead to a global state. So that also can be understood using Petri net. We can actually model those behaviors using this kind of Petri nets, the states and transitions. So in order to explain these situations, I will take a few examples and then show you how Petri net can be used for the behavioral modeling of systems. I will take a very familiar example, which is a traffic signal. Basically we all know that traffic signals are to be synchronized with other signals. Suppose you have a junction and then you want to show the signals on both sides, so you will be having a signal at this point and a signal here, of course here also. So these signals need to be synchronized, because there is a green signal here, then this always should be a red signal on both sides, and when this should change, this red should not change to green unless this green has changed to red. So this kind of concurrencies and synchronization need to be brought into the system, and we need to test that synchronization and then the concurrency using transition. So what kind of transition and what kind of control need to be put in place to ensure that there will not be any problem with the signals or there will not be any issues of synchronization. So this can be modeled using Petri net by showing different states and places as well as the transitions. So we can actually represent the signals. So you can show that one side signal, that is you have a red signal and you have a green signal and an orange signal. So this is the normal three signals, so red, green and orange. So these are the places. So we put, sorry, these are orange. I will write it outside because we need to show the tokens inside. So this is red, this is green, and this is the signal 1. And similarly we have signal 2 also. We have red signal, then we have the green signal, and then we have this orange signal. So red, green and orange, and we need to have the transitions, because when want to change from red to green you need a transition. So we will represent that transition here, then green to orange, one transition, let me represent it here because it is easy to represent the transitions. So this is the T1A, which actually shows the transition from red to green. So you have a transition from red to green, so it will be like this. So this is the flow of data. So this is transition A, T1A for the first signal, transition 1 for this, and then you have a transition here T1B, which actually shows the transition from green to orange, and then you have one more transition from orange to red. So let me show this transition here, T1C, which actually shows this transition from here. So this actually represents the transition and the places of a signal. You have red, green and orange, and you have this transition 1A, 1B and 1C, which actually represent the transition from one state to the other state, and we can have the tokens to represent the present state of the signal. In the same way you can have this transition here also. So here you have the T2A and you have this T2B, which is between T2A green to this is T2B, and then you have this T2C. So this is again the transition. So you have this red to green and then green to orange, then the transition from orange to red. So these are two independent signals. So this is signal 2, this is signal 1. What we need to do is to show the synchronization of these signals. So we cannot have two green signals at the same junction. So we need to ensure that when the signal is red here, then only that should be green, otherwise if this is green, that should never become a red signal. So how do we actually represent that situation using the tokens or the place values? So here this is the transition which actually moves from red to green. So red to green cannot be done unless we ensure that this is red. So we need to have some kind of another input over here or another place which actually connects to this, and when we have tokens on both this red and the other one, then only this can actually change to green. So we will provide another place here which actually connects to this T1A. So you can see that this T1A, the transition is connected to two places and both are actually coming to this T1A. That means there should be token available at this point and this at this place and this place in order to activate this transition. So that is the first condition. The same way for this also, for T2A, which actually transfers from red to green, that also should have 2, because when this is green, this should not change to green. So from red to green it should not happen. So therefore we need to ensure that this transition has to check what is the status of this particular signal. So we have another connection over here. So this transition has got two places connected, and both should have the tokens in order to make a transition from red to green. And then we need to ensure that once this has become red, then this has got a value, because when this is red, then only this can change to green. So we will have a place value connected to T2C also, similarly T1C, which actually gives a token back to this particular place. That is, whenever this orange has gone to red, then there will be a token available here. Similarly, when orange has become red, that token will be available here. That means when the signal is red, then only there will be a token over here. That means you can have a change from red to green in the other one. So we will represent this here. Suppose you have an initial token available here. Suppose this is the initial situation. You have a token available here and a token available here. That means both are red. When you have a token available here, that means both are red signal now. So you have a red signal here and a red signal here, so you have a token over here also. So now there is an option that you can actually have a T1A transition or T2A transition. So one of the signals can actually go to green, not both. Once you have this T1A activated, suppose you activate this T1A, the transition is activated, then immediately this token will be given to green and this token will be released from here because this is only one output. So this token will be released from here to this point. Now this is green and there is no token over here, therefore T2A cannot change. So T2A, that this transition cannot happen, that means this red cannot become green unless the token comes back to this position. So now this green is there, so the present position is that one signal is red, the other one is green. Now we have a transition here, suppose we go for the transition here, this token will be moved to here, that means orange will be activated. So this place has got a activation now, so the signal is orange now. Still it cannot change to red green because there is no token available here, and there will be a token available only when we have the next transition. So when we have this transition, suppose we activate this transition now, then this token will be given here, move to here as well as to this point, this place, because now we have this transition is connected as an output to here. So whenever there is an input coming to this, both these places will be getting a token. Now this has got a token, so the token is there and this signal is red. So at this point you can see that there is a token available here and a token available here also there is a token available, therefore we can actually activate this transition. So this signal is red and therefore we can activate this transition. Again this token will be removed and this token will be passed to this one. So the token from red will be passed to green. You can see that now one signal is red, the other signal is green. So again the same way we will do the transition. So this transition, the token will be passed to this, and when this transition is made, you activate this transition, this token will be moved from here, it will go to here as well as to here. So when we activate this transition, you will be getting the token at here and here. Now both the signals are red, therefore we can have the next transition from here. So unless this token comes back from here, this cannot activate and this red signal cannot change to green. So this actually shows that there is a synchronization between these two signals in order to ensure that there is no issues with the synchronization. Basically when one signal is red, then only the other will change to green. So this is one way of representing this synchronization using Petri net. So this is a traffic signal where we have different signals. Of course you can actually have multiple signals if you have more signals. Here I have shown only straight direction motion. So if you have a turning to right or turning to left and then taking U-turn, all those signals are there. We can actually incorporate all those scenarios and then see what kind of synchronization we need to ensure. So depending on that we need to include additional places so that the tokens can be distributed in such a way that there is proper synchronization and there is no issue of overlapping of signals or there is no other problem associated with the concurrency and synchronization. So this is one way of modeling the dynamics of this particular behavioral dynamics of the signal using Petri nets. The same way we can actually represent many other situations also. I can show you another situation where we have a restaurant and customers and basically people who actually serve. How do we actually synchronize the behavior of these customers and servants, and how do we actually optimize the use of these people by having proper synchronization of their activities. As you can see in the figure over here, so we have shown that there is a one waiter and two customers waiting for the customer, and so there is a waiter free. So now if you want to represent this situation, we can have different situation that the waiter can actually take the order from one customer and then he can give the order to the kitchen and then wait for the order to come, and then he can serve the customer and then order from the next customer, or he can take order from customer 1 and place the order to the kitchen, and then he can take the order from customer 2 and then place the order, and whenever the food is ready he can serve customer 1 and customer 2. So how do we actually represent this kind of scenarios using Petri nets? So as I mentioned, Petri net can actually shows all the dynamics, behavioral dynamics, and can show the concurrency and the synchronization. The same way we can use this situation also, we can represent using Petri net. So you can see here, so we have two scenarios we are representing. The scenario 1 is that the waiter takes order from customer 1 and serves customer 1, takes order from customer 2, serves customer 2. The customer 2 will be waiting till the customer 1 is served. The second scenario is that the waiter takes order from customer 1, takes order from customer 2, serves customer 2, and then serves customer 1. So this is the another scenario. Of course you can have many other scenarios of various situations, and then try to see how do we actually get those scenarios represented using Petri nets. Just for example, I am showing two scenarios. So this is the scenario 1. So initially both the customers are there, you can see the tokens at these places. So you have this token customer 1, then customer 2, and then there is a waiter who is free here. This transition, that is taking order, is shown by this transition, and then this taking order from customer 2 is shown by this transition. So you can see here this transition is connected to two places, so customer 1 and waiter free. So this transition can take place only if there are tokens in these two places, that is customer 1 and waiter, there are tokens available, then only it can be transition can take place. Similarly for the customer 2 also you need to have these transitions, and when this transition takes place there are two tokens coming over here. So when this transition takes place, as you can see, it is connected to two places, that is wait as well as order taken. So these two places you will be having tokens, and once you connect this one, you can see the serve food is connected to tokens, again waiter free and food is available. So these two are needed for this transition, or the customer is waiting and the waiter is free, then only that transition can take place. So the relationships, actually what particular relationship is needed for that transition can be represented using these arrows and the tokens. Now let us see how this is taking place. So you can see that the order is taken, so therefore the transition is taking place, customer is waiting here and the order is taken. So we have these two places with tokens now, because this transition takes place, you have this customer waiting here after the order is given, and the order is taken from the customer, that is completed. And now once the order is taken, that has to be informed to the kitchen, or it has to be placed to the kitchen. So that is this transition. So the waiter will need to give this order to the kitchen, so he will be giving this order to the kitchen, that is this transition. So you can see here, so once he places the order, actually the token goes back to the waiter. So once he ordered the item to the kitchen, then the waiter is free here. So here now the waiter is free, this customer is free, and this customer is waiting. So the waiter has got an option either to take the order from customer 2 or to wait for the item to be ready so that he can serve food. So you can see that to serve food for this transition, you can see this is the waiter should be free, and then there should be food should be ready. So now waiter has option to take the customer 2 order or wait for the food to be served. So here in the first case it is actually serving food and the customer is eating, so the place is taken, the token is given there, and therefore the waiter is again free after the serving of food. So the customer is free now, he can take the order, second order. So he is taking the second order, customer 2, and you can see the tokens are moving here, order is taken and the customer is waiting, order is taken, and then tell the kitchen about the order. So this is activated, so you will be getting the transition, and then you will get the serve food and the customer is eating and the waiter is free now. So both the customers are having food and the waiter is free. So this is one scenario where we can actually represent the dynamics or the behavioral dynamics, what is happening inside in that particular scenario. So you can have any number of customers and any number of waiters, so we can actually show the complexities also with some weighted arcs that I will explain later. But in this case we can see that this scenario can be represented using Petri nets and the place values and the tokens. So in the scenario 2 it is almost similar, except that the situation changes. So here the waiter and customers are free, and then actually he takes the order from customer 1. So customer is waiting and the order is taken, and that is informed to the kitchen, and the waiter is free and one customer is waiting for food, the other customer is waiting for to place the order. Now you actually take the second situation, the waiter is taking order from customer 2 and then places the order to the kitchen, and then both the customers are waiting and the waiter is free so that he can actually serve food. Now the waiter is free, so he will serve the food to one customer, so serve food to customer 2 and then serve food to customer 1. So this is where how you actually represent the scenario. So any scenario can be shown like this way. So we can actually show the what kind of concurrency is needed and what kind of synchronizations are needed, that can actually be represented using this kind of Petri net. That was one example, and there are a few more examples which actually shows the complexity of the Petri net. Here you can see, as I mentioned, the Petri net can be used for various scenarios. So we can actually represent a sequence of events. As you can see here, you can have events E1, E2, E3 represented, and the places and transitions. As we have the places and transitions, we can actually represent it using in a serial way. So we have these places or the events. So you can have an event 1 or the places, then you have a transition, then you have an event. So this kind of serial activations, sorry. So this is E1, E2, then transition 1, transition 2. So this is basically a serial sequence of events, so that can actually be represented using this kind of Petri nets, or you can actually go for the concurrent executions. So this actually shows the executions, how the place values are changing. So if you go back, you can actually see this. So when you have the transition E1 is happening, the token is transferred to the next one, then you have this token next one happening, then again the token is transferred using every transitions. So this is one way of showing the sequence of events. And then the concurrent executions, you can see in the picture here, the concurrent executions also can take place. By concurrency you mean that you have this transition, so we have actually these concurrent activities, you can have this kind of transitions and events. So the places, the transitions can actually happen like this. So this actually shows the concurrency of the events. So you have one event and then you have many events going at the same time, and of course you can actually, if they come to one stage at a later stage, then actually you can have the same output from here. So these events will happen concurrently, and once these two are ready, then only this transition will take place and finally it will give an output. So that is the sequence or concurrent execution. So this is the serial one or sequence of events, and this is the concurrent event. The concurrency of events or concurrency of executions. Same way, this can actually be again shown through the animation. You can see the E1 happening, so the tokens are given to the next two parallel execution chains, that is the concurrent events, and then E2 and E4 take place, then you pass the token, then again E3 happen, E3 and E5 pass the token. So like this you can have concurrency of events. These are the sequence of events and the concurrency of events, and apart from this we can actually have non-deterministic events like conflict, choice or decision. So this also can be represented using this kind of Petri nets, that is you can have a choice of either E1 or E2 or E3 or E4 like that. So you can actually choose an event based on particular conditions, you can actually make a choice also, that also can be represented using Petri nets. So here you can see that you can go for E1 or E3, E1, E2 etc., or you can go for E3, E4 in that level also. So this also can be represented. So in this case if you pass the token to E1 or E3 can be executed. So in this situation what is shown here, so only one of these transition can take place, then this will happen, E1, E2 etc. will happen, or if this is started then E3, E4 etc. will start. So not concurrently this will happen, so only one group will be executing. So as you can see here, so if E3 event is happening, then E1 cannot happen because there is no token available here. So E1 cannot happen unless the token comes back to this position. So E3 will happen, then E4 will happen, and then it will continue like this until when it reaches one point where the token from here is returned back to this position, event cannot start. So that is the choice for a particular situation. So this actually shows the second one. So once event is activated, then E3 cannot happen because the token is not available, therefore E3 will not happen, then E2 will happen and then continue. So that is about the structures where you can have choices and various options to execute. Now there are different other net structures also, as you can see here. In this case, this is a synchronization which I already explained. So the synchronization will happen only when this event can happen only when these tokens are available in all these cases. So if the tokens are not available here, event cannot happen. That means this event will be synchronized with the happening of all these 3 incidences. So all these places should have token in order to activate this. So that is 3 are ready, then only event can be executed, and it will be going, the token will be moved to the next one. So that is the synchronization structure. Then the next one is the concurrency. So synchronization we saw, then synchronization and concurrency also can be introduced through structures. So this is the synchronization and concurrency structure. So this actually shows the synchronization. So this E1 will synchronize with the happening of all the 3, and the concurrency, when event is activated, all these will concurrently start, all these will be having the places. So that is the synchronization and concurrency of the system. Again you can see here. So you have the transition E1, this will go to all the places, will be having the token value, and therefore you will be getting activation of this, and that will be the concurrency of the system. So that is how the synchronization concurrency can be represented using Petri nets. Now we will take another example where we can show all these concurrency sequence of activation as well as concurrent activation and synchronization. We will take another example where a producer consumer system which consists of one producer and 2 consumers and 1 storage buffer with the conditions. In this case we have a producer consumer system where we have 1 producer and 2 consumers and 1 storage buffer. So how do we actually synchronize the activities of the producer, the consumer as well as the storage? We need to ensure that the producer is enough for the consumer, and if the consumer is not taking, it is going to the storage, and the storage is not overflowing. So how do we actually represent this concurrency and the synchronization of these events? That can be represented using Petri net. So the conditions for this are, the storage buffer may contain at most 5 items. So storage buffer cannot have more than 5 items, and the producer sends 3 items in each production. So whenever the producer makes one production, it will be having 3 items, and buffer can have only 5 items stored, and at most one consumer is able to access the storage buffer at one time. So only one consumer will be able to access the storage buffer at one time, and each consumer removes 2 items when accessing the storage buffer. So whenever a consumer access the storage buffer, he can take 2 items, but only one consumer can access it at one time, and one producer can produce 3 items at a time, and the storage buffer has got a maximum capacity of 5. So how do we actually ensure that there is no overflow of the buffer as well as the storage, as well as the producer is not producing more than what can be stored or consumed, and how do we ensure that consumer gets the items whenever it is there, or whenever the customer wants, he gets some item. So how do we ensure this condition? We can actually represent that kind of a scenario using Petri net. So the Petri net for the system is shown here. So here you can look at the Petri net. So this is the producer, this is the storage, and this is the consumer. So we have consumer place this one, and this is the consumer 2, and you have this producer, then it is ready for transfer to the storage. So this is the storage with a place value of 5. So here you can see that the storage can have a maximum 5 items. So that is why K is given as 5. So this is another kind of Petri net where you have the values for the places as well as for the arcs. You can see here these are the arcs which actually represent the transition from this state to this state. So the value is given as 3. That means you can send 3 at any time to the storage. Similarly, the consumer can actually take 2 at any time. That is why K is equal to 2 in both the cases. So here it's K is equal to 2, and only 2 can be removed from here by the consumer, that is why this value is 2. So whatever any transition takes place, only 2 will be moved from here, though there is a value of 5. So 3 can come at any time and 2 can be removed, and these 2 can actually take 2 each, but only 1 at a time, and it can be consumed. Once you consumed, again they can take the items. So this is the situation. You have the producer producing items and then going to the storage, and then it is consumed by the consumer. Now look at this, how do we actually show the dynamics or behavior of this system. You can see here, so there is one producer, that is k is equal to 1, there is one producer who actually produces 3 items. So this is k is equal to 1 producer, and this is 3, k is equal to 1 is this producer 1, and this is 2, k is equal to 1 is another producer. So he can actually produce, this is 3 items at a time. Now the 2 consumers are free and the producer is also free. So you have the producer here idle and the consumer here also ready to consume. Now the first thing is basically the producer will produce some item, so it will actually producing the item, and then the item is ready for taking. So that is the token is transferred from here to here. So the producer is given one item, it is ready for transport, and then that actually transferred back to the storage space. So this one producer actually produces 3 items, that is why once he sends the item to the storage, there is 3 places available, 3 value of this place is 3 now, and the producer is again free to produce. And now he can produce more, but it cannot be sent here, because next time if he sends it will be another 3, but it can take only 5. Therefore we need to ensure that before he sends this item to here, this has to be accepted by the consumer. We will see how do we actually represent this scenario. So once we have this, he can actually produce further and then it will be ready, but it cannot be sent. You can see here this cannot be sent, because if you send it, it will overflow. So though he is ready to send, he cannot send it because it may overflow. Therefore one consumer has to accept the product. Therefore we have to accept the product. So the one customer has accepted it, or consumer accepted it, and that is why he has accepted 2 items here, and then one place value is 1 here, because one consumer already accepted the item and another consumer is free. And now he cannot accept further because there is only 1 item, so he cannot accept, this cannot be accepted, because there should be 2 in order to activate this one, there is only 1 at this place, therefore it cannot be activated. So we need to activate the producer again, so the producer should actually produce it further. So that is why it is already produced, and that should be sent to the storage space. So it actually goes to the storage, and then storage has got 4 now. Again we can have another consumer accepting it. Now we can actually have 2 consumer accepting it, because there are 2 plus 2 4 items available, but there is only 1 consumer ready for accepting it. So only 1 consumer is available, so he can actually accept it. So it has gone back to the accepted, and then this both the consumers accepted the item. So you have this both consumers accepting the item, and there are 2 items already available, and now the producer is still able to produce 3 and send it, because we can have another 3 in the storage buffer. So we can actually either producer can produce, or the consumer can actually consume and accept it also. So the producer is again producing one more set, so he is ready and he can actually send it to the storage. So you can see that now the storage is full with 5 items already filled in. Now producer can still produce, but it cannot be sent, but there are no consumers also available to accept it. So now it is a full condition, consumers are not available to accept it, because you can see here the consumer, there are no tokens available, so this transition cannot take place. So unless the consumer consumes the product, it will not be taken from the storage space. So we need to ensure that at this situation the consumer consumes or the producer stops producing the item. So here see that producer is free, but we are actually making the consumer consume the item, and then consumer is made available. So now one consumer is free to accept another 2 item. Therefore you can actually make sure that this consumer accepts further item from the storage before the producer goes for its production. So you can see again 2 are accepted by the consumer, 2 items are removed from the storage. So it actually accepted and then can consume, and you can continue the cycle again. So here the place values are given, so that is one important point about this particular Petri net. you can see that the place values, there is one producer produces 3 items, so that is the place value here. Whenever he sends 3 items, so this is the 3 value, and then from sending accepting only 2 can be accepted, so that is why you have 2 place value. This actually shows that the number of tokens to be handed or to be moved is equal to the number of the value of k shown here. So 2 will be transferred, and then you will be having the accepted also, you can actually have accepted 2 and that will be consumed, and then the consumer will come back. So this way the scenario of concurrency as well as the sequential activations can be represented using Petri net. So this is one case where we can have complex scenarios presented using Petri nets, where we use the weighted arcs as well as the place values to represent the capacities of the buffer or the producer or the consumer, how much they can accept from a particular storage, and how much they can produce, and what will be the upper limit of storage space. All those things can be represented using this kind of weighted arcs as well as place values. That is the importance of having this kind of Petri net. So as you can see here in this Petri net, every place has a capacity and every arc has a weight. So we have a capacity as well as a weight for the arc, and this allows multiple tokens to reside in a place to model more complex behavior. So this actually helps us to have multiple tokens to reside in a place to model the complex behavior of the system. As you saw in the previous one, there were multiple tokens in the picture. You can see these are the multiple tokens in the storage space. You can have up to 5 tokens, that actually represents the capacity of that particular place. So this can actually go maximum 5, and then we have to remove a few tokens before we actually fill this with the token. Okay, now there are various other Petri nets also. I explained that in the simple Petri nets we will not be having the weightage or the place values. There is no weight for the arc or the place values for the number of tokens for the places, and in the some other or the more complex Petri nets you can actually have the arc weights as well as the place values, the number of tokens. But then if you want to have more complex system behavior to be modeled using Petri net, we need to go for the complex Petri nets, where we call it as high level Petri nets. In this case there will be colors holding complex information. So you can have different colors for the place values or the tokens. So you can have black token, red token or green token, which actually represent different scenarios. So that can actually be incorporated in the Petri net. And apart from this we can have timed Petri net also. So in the previous cases we did not include the timing of the system. So how much time it takes to make a production and how much time it takes for the consume the product, or how long we can keep a product in the storage. So that is not incorporated in the Petri net. But in more advanced Petri nets we can actually incorporate those values also, the timings also. So time delays associated with the transitions and or places can be incorporated, and fixed delays or interval delays can also be incorporated, and the stochastic Petri nets which exponentially distributed random variables as delays can also be incorporated into the Petri net. So basically it shows that any complex system with any variations in terms of behaviors or in terms of the capacities or in terms of time can actually be modeled using Petri nets. So these are very useful for system design, because in complex systems we may encounter with various scenarios. So some scenarios we will be having the situation where we need to represent the behavior without worrying too much about the timings. But in some scenarios we are more worried about the time, especially when you are looking at something which actually to be executed in a particular time, or there is an urgency to execute some of the tasks within a particular time interval. So in such situations we need to look at the time involvement also. So all these scenarios can be easily represented using Petri nets. So this actually will be a very good useful tool in the design of systems. If you want to know more about the Petri nets, you can actually see these references. There are a lot of references available, so you can go through any of these references. Murata 1989, and then this Peterson 81, then of course Racing and Rosenberg 1998, and there are a lot of internet resources available also. You can actually search for Petri net, you will get a lot of examples and a lot of case studies. So you can actually learn more about the use of Petri nets for the system design, or practical examples can be easily obtained from these kind of resources. So with that we have come to conclusion for the graphical modeling techniques. So there are few other techniques also. Actually we talk about, when we talk about the modeling, one is the graphical modeling techniques, basically looking at the behavioral dynamics of the system. So they do not really take into the actual system dynamics, or more into the engineering dynamics will not be taken into account. So there is 3 methods what we discussed: the data modeling, the process modeling and behavior modeling. They were mainly to look at the behavior of the system and how the data transmission takes place, how the relationships are taking place, and how the behavioral dynamics takes place. These modeling methods can be used for analyzing those behaviors. But if you want to know more about the system dynamics, the time response of the system and how fast the system will respond for a particular input, and what are the physics involved in the system, and how do we model the physics behind the system. So this can actually be modeled using system modeling and simulation techniques. There are various modeling and simulation techniques to look at the system dynamics, and those methods and the methodologies for system engineering we will discuss in the next class. So till we meet, goodbye to all of you.